Hey guys, this is the inverse trig functions lesson. We've actually got two lessons on inverse trig functions. And we know if a function is a one-to-one function, that means it passes the horizontal line test. Then we know its inverse relation is also a function. For sine, cosine, and tangent, we need to restrict the domains of each function to discover the properties of the inverse functions. And right here on the first page of your notes are the properties and the domains for each one of these expressions, whether you're taking the sine of an inverse or if you're taking the inverse of a sine. Those domains are going to be restricted in different ways. And without spending a lot of time going through them, we'll just graph and take a look at those features. Here's some helpful things to remember. A function has an inverse if it passes the horizontal line test and it's one-to-one. If you can restrict the domain, then you can find an inverse function. Inverse functions have symmetry across the line y equals x. That's the identity function. And you can graph an inverse function by switching the ordered pairs of the original function. So for example, if 2, 4 is on my parabola, then on the inverse, 4, 2 is on the inverse. And 1, 1 is on both of those functions, just as 0, 0 is on both of those functions. So the same holds true for trig functions. Remember that a function will have an inverse if it's one-to-one. Functions are one-to-one if they have only one x value for every y value. A function f of x with inverse f inverse of x has the following characteristics. If we do a composition of the inverse with the function, we'll get the identity graph x, or alternately the other way around, if we do the composition of the function with its inverse, we will also get the identity function x. If they're both equal to x, it has to be both compositions. Then we know that they are inverses of each other. Also, the domain of a function is equal to the range of its inverse, and the range of a function is equal to the domain of its inverse. In the graph of a function and its inverse are symmetric with respect to the line y equals x. And finally, if a function f of x has an inverse, the equation of the inverse is x equals f of y. See how we're interchanging? What was y is now x, and what was x is now y. The solution of this equation is y equals f inverse of x. So let's jump right in. First, we're going to plot sine x between negative 2 pi and 2 pi. And we're going to see it is not a one-to-one function. So let's jump right in and do that. So the sine curve, we know, has the key points of intercept max, intercept min, intercept, and the period is 2 pi, and the maximum and the minimum are at 90 degrees and 270 degrees, and there is one original cycle of sine. If we go backwards, we have a min, an intercept, a max, and an intercept, and we've graphed between negative 2 pi and positive 2 pi. Now, that function fails the horizontal line test. And you notice that the range is between 1 and negative 1. Our range is between 1 and negative 1. In the domain, that will give you a range value of positive 1. Let's go look at that. I can get a range value of negative 1 right here, and I can get a range value at positive 1 right there. So if we consider this little portion of the parent function, what domain will give you a range value of, we're missing a line here, of positive 1 is pi over 2, and what range value will give you, what domain value will give you a range of negative 1 would be at negative pi over 2. So we're missing a line right there on our slide. We're going to use the last two answers to restrict our domain for the sine of x. And this will become the range of our inverse function. So if you summarize that, if your function is the inverse, where your domain is from -1 to +1, and your range is from -half a pi to +half a pi, what will that graph look like? So here you can see when we're at 0, 0, we still have 0, 0 on our function. But here at negative pi over 2, our ordered pair, negative pi over 2, -1, is going to be reversed on our graph. So we would have -1 and negative pi over 2. And on this end, pi over 2, +1, would be interchanged to be +1, positive pi over 2. And at negative pi over 4, our value would be square root of 2 over 2 in the negative. So we'd come over here, negative pi over 4, and we'd go down square root of 2. I'm sorry, take that back. We would go left, negative square root of 2 over 2, which is about 0.7, and down to pi over 4, negative pi over 4. And then on this side, instead of positive pi over 4, positive square root of 2 over 2, we would interchange that, and we would go over to square root of 2 over 2, again 0.7-ish, and up pi over 4, which gives us that little smooth curve for our inverse function, and I can show that to you here on our calculator. So in example 1, remember when we're looking for y equals sine inverse of x, that means our x value is the sine of y between -1 and +1, and our range is between negative pi over 2 and pi over 2. So when you read the statement sine inverse of 1, that's really asking us to find the value where the sine is 1. So if we rewrote that using this definition of up here, the sine of some y value is 1, and that y value is pi over 2. So it's answering the question, where will you find the sine equal to 1? And that would be at the angle pi over 2. In this case, sine inverse is -1/2. We're looking again at the range. So we want to answer the question, where will the angle be -1/2? But remember, I'm asking you to think about the range. We're only allowed on the unit circle to consider from pi over 2 to negative pi over 2. So we can't go over here to look for that angle. And the sine is -1/2 if we have a negative rotation down here. So our answer is going to be a negative angle. Y would be negative pi over 6. At what angle is sine -1/2? If we did a positive angle rotation, we would be outside of our restricted zone. The answer would be positive 11 pi over 6. But remember, we're limited to our answers being somewhere between positive pi over 2 and negative pi over 2, and this answer fits that restriction. On part C, we're looking for the angle where sine is the square root of 2 over 2, and the angle where sine is square root of 2 over 2 would be when the angle is pi over 4. And then this last one, we need our calculator, and sine inverse is right there on the calculator, and we want the sine inverse of 1/3. I'm going to put a decimal there, so it's going to give us a decimal answer, and that decimal answer is about, I lost it, 0.3398. And let's see if it'll give us the exact answer here. Sine inverse of 1/3. And you can see it does not give the exact answer there. Okay, moving on. inverse cosine function, first we're going to plot y equals cosine of x on the interval from negative 2 pi to positive 2 pi. And we want to know, is the function 1 to 1? Looking at the graph of the cosine function, you can tell it is not 1 to 1. It does not pass the horizontal line test, so the answer is no. But we can restrict the domain so the graph will pass the horizontal line test. And here's a little help. To do this, first find the range of cosine. Well, the range of cosine goes between negative 1 and positive 1. And what domain value will give you a range value of negative 1? That would be pi. And what domain value will give you a range value of positive 1? That would be 0. So we can use the last two answers to restrict our domain for cosine of x. That domain will become the range of the inverse cosine function. So when y is the cosine inverse of x, where the domain is between negative 1 and positive 1, and the range is between 0 and pi. Now we can plot cosine inverse on the graph. And here's our restricted area, so we're looking from 0 to pi, and with the ordered pair 0, 1, on our inverse function, we're going to graph the point 1, 0. And at pi, negative 1, we're going to graph the ordered pair negative 1, pi. At pi over 2, or 0, so on the y-axis, the coordinate would be 0, pi over 2, and that's going to have a curvy look like, oh, that's not good. That's a little bit better. It shows up better on the calculator. It's a smooth curve, kind of like a inverted S curve there. And we'll give these a try. So same as sine inverse, remember y equals cosine inverse means x is the cosine of y. And we're restricted from negative 1 to 1 on the domain, and we're restricted 0 to pi on the range. So cosine inverse of 0, remember we're thinking about the range. We want to answer the question, where is the angle for cosine being 0? And that happens at pi over 2. And then this one, where is the cosine? At what angle is cosine negative 1/2? And that would be in this top half of the unit circle. That would be over here at 2 pi over 3. So our angle is 2 pi over 3. And the angle where cosine is square root of 2 over 2 is going to be pi over 4. And then this last one here, that find the angle where cosine is 1/3. And this would be an estimate on our calculator. So the angle where cosine is 1/3 is going to be 1.23095 radians. So if you wanted to, you could answer in radians, 1.23095. And if you wanted to convert that to degrees, then we would want to multiply that answer times 180 and divide by pi. And that value as a degree would be about 70.5287 degrees. And then the last one we'll look at today is inverse tangent. So again, we can graph tangent and it will not be 1 to 1, so we can restrict that domain. And we know tangent has a vertical asymptote at negative 90 and at positive 90. We know that there's an intercept in the middle, and halfway we got a negative 1, and halfway we got a positive 1, and it's that smooth curve this way. So if we did other branches, you can see it's not going to be 1 to 1 because it fails the horizontal line test. So it is not 1-to-1. We can restrict the domain to only one period, so the graph will pass the horizontal line test. And if we just ignored this branch and this branch, we have gone through every value of tangent. And that's going to make our tangent go between, inverse will go between negative pi and positive pi, negative infinity and positive infinity. And the range would go between negative pi over 2 and positive pi over 2. So instead of having vertical asymptotes here, we've got those vertical asymptotes. We've got horizontal asymptotes on our inverse. And our function's still going to pass through 0, 0. And we would have 1 pi over 4. And we would have negative 1, negative pi over 4. So the tangent function has a little bit different look on the inverse tangent than the other two do. So these go on forever. The domain is forever, where sine and cosine stopped at either negative pi over 2 or 0 and pi. So looking at tangent now, the inverse tangent is 1 where the angle is 1, and that's at 45 degrees because we're looking at the range. And the inverse tangent is negative radical 3 where the y value has negative pi over 3. Our angle would have to be negative pi over 3 for tangent to have that ratio. And then the tangent inverse is 0. What angle has tangent is 0? That would be at 0 radians. And here we have one for estimating the tangent, the angle where tangent is 5, and tan inverse is 5 at 1.373 radians, about 1.373 radians using our calculator. Okay, couple more calculator questions are next. So these, again, we're using our calculator to estimate the angle where sine inverse is negative 0.74. So that would happen at 0.833 radians, negative 8337 radians. And 83307. 8330, whoop. 83307. Now this one ought to be a little suspect. If you think about it, this is the range, and we're defined between -1 and +1. So hopefully our calculator is going to tell us this isn't possible because it's outside of the inverse function domain. So cosine inverse of 1.5, because remember it's asking us what angle will cosine be 1.5. Well, there is no angle. It's not real, not a real result. And then this one, sine inverse of sine of 2.5. So there's a couple of ways we can approach that. Either straight with the calculator, sine of the sine inverse of 2.5 pi and the calculator tells us that's what, 7.85. So think about it that way. It's 7.8539. 39. Or you can also think about it this way. If we go in here and think about this inner portion, the sine of 2.5 pi is like taking one full revolution and another half of a pi revolution. The sine of 2.5 pi is 1, right? So the sine inverse of the sine of 2.5 pi is 1, is what it's asking us to do, and sine is 1 at pi over 2. So a better answer would be to break this apart into two pieces. Do the inside part first, thinking about the sine of 2.5 pi would be like 2 pi plus a half of a pi, and 2 pi, if you go all the way around to 2 pi radians, that's a 0. So I'm really asking for the sine inverse, where sine of half of a pi. And sine of half of a pi is 1, and the inverse where sine is 1 is half of a pi. So this cancels this, and that's getting back to those properties on that first table that we had. And the same thing here, the tangent and the tan inverse, they're going to cancel each other. Tan undoes the inverse, and our calculator should tell us -4. So tan, the tangent of tan inverse, so the angle where the tangent is 4, and we want the tangent of that angle, which would also be 4, or -4. I forgot to hit the negative in my calculator. This would be -4. So again, because our domain and range are okay, these two cancel each other. That just wipes out the other one. It's like taking the square root of a value and then squaring it. The square root cancels the square. They're inverse operations, and they undo each other. Okay, so in this case, I need to back up just a minute. Something ran across my mind. In this case, if I was just using a calculator, this answer would not be an appropriate answer because it's outside of our inverse function domain. Remember, if I'm doing sine inverse of sine, so we can go back to that original table on that first page. We got sine inverse of sine. Our answer has to fall between -1.5, 1.57, and + 1.57. And on that calculator prompt, this is definitely not between -pi/2 and +pi/2. So that's why I had to break that down apart and come up with a better answer, because my answer had to live within that domain on the inverse function. So you just have to be aware of that. And then in example 5, we want to think about these without the calculator. So again, like I said, if you have an inverse, you're on restriction, and you can think about the cosine. You can think about cosine as quadrant 1 and 2. I'm restricted with an answer between 0 and pi, and cosine is pi/2. Cosine is square root of 2 over 2 at pi/4. That's well within my domain, and there's my answer for that. Tangent is restricted like sine is, and we can only answer in quadrant 1 and quadrant 4. Our answer has to be a value between -half a pi and +half a pi, and tangent is opposite over adjacent. So I would want an angle where I have, or sine over cosine, if you think about it that way, or the y value over the x value, if you think about it in that case. And I need to come out 1/2 here and go down -square root of 3 over 2. So when I divide sine by cosine, I'm going to end up with -radical 3, when the angle is negative 60 degrees or negative pi over 3. So you can reason through it that way. And then here I am again. Cosine inverse is restricted between 0 and pi. And what's going to happen, cosine inverse, where cosine of this angle, this is a radian angle, so it's not too big. I can have cosine of negative 1.1, but this cosine cancels this. My answer has to be an answer between 0 and pi, and if these inverse functions cancel each other, like a square and a square root, then my answer would be 1.1, not negative 1.1, because cosine is an even function, so 1.1. And we can verify that with the calculator. So cosine inverse of the cosine of negative 1.1 is going to be positive 1.1, since cosine's an even function. Okay? In example 6, we can also evaluate inverse functions by drawing pictures of triangles. So in this case, we want to draw the triangle. See, sine inverse, this is a triangle. So I'm thinking there's an angle where the sine inverse is negative 1/2, or you can think about it, the sine of an angle is negative 1/2. Can you draw that triangle? Sine is opposite over hypotenuse. This would be negative, and that side would have to be radical 3, since the Pythagorean theorem would have the square root of 4 minus 1. That would be radical 3. And then after we draw the triangle, now we can answer the question, what's the cosine of that angle you just drew? This is my angle. Sine inverse is negative 1/2. What's the cosine? That would be adjacent side divided by hypotenuse, and the adjacent would be radical 3, and the hypotenuse would be 2. So the answer to our question would be radical 3 over 2. And that's one of our famous right triangles. Example 7 is just another one, just similar to that. So we're looking for a picture where the cosine has the properties adjacent to hypotenuse, where adjacent is 5 and hypotenuse is 13. So adjacent to hypotenuse is that angle, and your job is to find the missing side. Well, if you know from the Pythagorean triples that a 5, 12, 13 triangle makes 12 my missing side. If you don't know that, you can say a squared plus b squared is c squared and solve for b as the square root of 144 or 12. And then we want to answer the question. So we've got our picture drawn. That took care of all of this part on the inside. And we want to know what is the sine of the picture you drew with that angle theta. And sine is opposite divided by hypotenuse, and opposite would be 12, where hypotenuse would be 13. So the sine of the cosine inverse of 5/13 would be 12/13. And we have that finished. Now, our last example is a practical real-world application, and we have the bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. So I'm assuming this little piece in here is the screen, and we're 45 feet above the playing field. If this is the ground at the field, and that's where the screen begins. The screen is 20 feet tall. And as you move away from the wall, the angle formed by the screen at your eye is going to change. there is a distance from the wall at which the angle is the greatest. So we're going to say this is this distance. And assuming that this is a right angle, this is the angle that's going to be that subtended angle. We're going to call that theta. Let theta be the subtended angle. And we need to set up a relationship. So there's this angle. I'm going to put it in red. From the ground up to that top angle, that's theta 1. And from the ground up to the bottom of that angle of the screen, we're going to call that theta sub 2. And we drew that picture to show that angle. So we already have that picture drawn right there. Whoop, where's part C? Set up a relationship for the angles where theta equals theta 1 minus theta 2. So we had a relationship. I could say tangent. Let's go back and look at the picture here a minute. So we could say this first triangle is 65 feet. So let's think about that. I've got a triangle that's got 65 feet here from the ground to the top of the screen. That's our theta 1. And we don't know this. And then I have the other picture. That was the smaller angle. That was 45 feet from the ground to the bottom of the screen, and we called that theta 2. So we could say tangent is opposite to adjacent, and tangent is opposite adjacent. So we could say that theta 1 is the inverse of the whole thing over x, and theta 2 is inverse tangent of 45 divided by x, and the relationship would be theta equals tan inverse of theta 1 minus tan inverse of theta 2. So 45 over x. And then they want us to graph this in degree mode. So that's tricky. You've got to make sure your calculator is in degree mode. And I've already pre-done that to save time. Between 0 and 400 on the x-axis and 0 and 16 on the y-axis. And I found this to be the maximum after I used that maximum feature with my calculator. So what's this telling me? It's telling me when you're this many feet away, this is the degree. See, we're in degree mode. This is the degree that's going to be the angle with the greatest degree. So we could say that in words. When you stand about 54 feet away from the screen, roughly 54 feet away from the screen, the angle is the greatest. The angle is the greatest at 10.48 degrees. Okay? So a little practical application there. And that's the end of our first look at inverse trig function. The next lesson has a little bit more about inverse trig functions. See you next time.